Welcome back. In this session, we are going to discuss how to solve systems of differential equations that result into complex eigenvalues. So consider the differential equation for system of first order linear differential equations x dot equals to a x. Now let x of t be given by e raised power lambda t times vector u, where lambda is a complex root or simply complex number, i.e. lambda is given by a plus b I, where I is the square root of -1 of the complex unity. Now, and u is given by v plus I w it's a complex eigen vector whose real part is v and imaginary part w. Now, x of t is given by e raised power lambda t times u. Then it means that x of t will be given by e raised power, where this lambda we put a plus bi times t, and where this u we put v plus I w, just substituting the values of lambda and the values of u. Now, from laws of indices, if you have, so next step, this would be x of t is equals to e raised power at plus bti, and then times v plus I w. This is just opening these brackets. And then x of t will be e raised power at times e raised power bti into v plus I w. I'm just using laws of indices that a raised power m plus n is a power m, a power n. Now, we know that by Euler's identity, e raised power theta I is given by cosine of theta plus I sine of theta. So this is Euler identity. So which means that this term here, x of t, will be written as e raised power at. Now instead of writing e raised power bt I using this Euler's identity, we write it as cos of bt, because that's our theta, plus I sine of bt. And then we multiply by v plus I w. So that's what we have. So remember, e raised power 8 is just a number. So this can be written as x of t is e raised power at cosine of bt plus I e raised power at sine of bt. And then this will multiply by v plus iw. So this now, let's just open the brackets and collect real parts and imaginary parts. So x of t will be this by this will give me v e raised power at cosine of bt. This term and this term will give me plus I w e raised power at cosine of bt. This by this will give me plus I v e raised power at sine bt. Now this by this, I times I is I squared, and I squared is the same as -1. So I'll have a negative sign, and then w e at, and then sine of bt. Now collecting real and imaginary parts, x of t will be, so this real part, v e raised power at cosine of bt. This is another real part minus w e raised power at and then sine of bt, and then plus, let me factor out I, and then you have v, or let me start with w e raised power at cosine of bt plus v e raised power at and then sine of bt. Now, because every term has e raised power at, so i.e., I can write x of t equals to e raised power at into v cos bt minus w sine bt plus I e raised power at into w cos bt plus v sine bt. So this is the same thing as, so this is the imaginary, this is the real part of x, and then this is the imaginary part of x. So we can just say x of t is given by real part of x plus the I imaginary part of x. So then if we let x1 to be the real part of x and x2 to be the imaginary part of x, then it can be shown that the solution of x of t is the linear combination of x1 and x2. Hence, when we have complex eigen values, so lambda will be given by a plus or minus bi, then the solution to this system x dot equals to ax is given by x of t is equals to c1 times x1 of t plus c2 x2 of t, where x1 of t is given by e raised power a t into v cosine of bt minus w sine of bt, and x2 of t is given by e raised power a t into w cosine of bt plus v sine of bt. Remember, this is the imaginary, this is the real imaginary part of the x, and then this is the real part of the x. So this is what you need to know when you're solving a system of differential equations, which can be put in the form x dot equals to ax. And whenever we have complex eigenvalues, then this is how the solution looks like. In the next session, you'll do an example to illustrate how we do that on a specific problem. Thank you.